Hi, welcome to part 2 of comparing the derivatives. Remember, we were comparing the first derivative and the second derivative, the value, the derivative, or the slope, and the concavity. And in part 1, we used the graph of the derivative in order to get the original function. So let's take a look at another example here. We want to write the equation of a tangent line. Oh my gosh, there's a tangent line right there. We know tangent lines. We want to find the equation of the tangent line of this cubic graph at the point of inflection. So they are mentioning point of inflection, so we know that the second derivative, in this case, is going to equal 0. I know it's not going to be a d/e because this is a polynomial function. There's no places where the graph function will be undefined, nor the derivatives. So what we are going to do is we are going to need to take a few derivatives. So let's go ahead and start by taking the first derivative, and that's going to give us 6x squared minus 6x minus 12. And taking the second derivative, that's going to give us 12x minus 6. Now, I need to find the POI, so let's go ahead and do that. So the POI will be where the second derivative is 0. And if I set that equal to 0, this is not going to turn out nice. We get x equals 1/2. So let's see. We're ready now. So at x equals 1/2, we want to find the tangent line. So to get the tangent line, we need a point. So we need the value at 1/2. So let's see if we can do this. This becomes 2. 1/2 cubed is 1/8, so 2 times 1/8. Minus 3 times 1/2 squared is 1/4. Minus 12 times 1/2 plus 5. Now I did all the simplifying for you ahead of time. This becomes a negative 3/2. And so our point, therefore, would be x equals 1/2 negative 3/2. There's the point. Now we also need the slope of the function. So we need f prime of 1/2. And we took the derivative already. That's over here. So that's going to become 6 times 1/2 squared is 1/4 minus 6 times 1/2 minus 12. And again, I did kind of the math here for you. This becomes negative 27 over 2. So there's our slope. So we have our point and we have our slope. To write our tangent line, remember it's going to be y minus y1 equals m times x minus x1. So we would get y plus 3/2 equals to m negative 27 over 2 x minus 1/2. And there's our tangent line right there. Very easy to do. Everybody can do that. So this will be worth quite a few points because you have to find that point of inflection as well. You have to find the second derivative, find that possible point of inflection, find your point, find your slope in your equation. So this would be like a 5 or 6 point question for us. All right, for question number 3, this is kind of a neat little question about kind of the idea. It's of a derivative. So they're saying a function is continuous. If f of x is a continuous function defined on the values, such that the maximum value is 8 and the minimum value is negative 9, then which of the following must be true? So I'm going to draw a couple different examples here. And this is a better way to kind of think about it. So I'm going to do one. Let's do the maximum value is positive 8. I'll start that over here. And the minimum value at negative 9. I'll put that over here. So I can have a graph like this. And I'm just going to connect it. And let me take a look at another example. Ready? What if I switch it around? My maximum value is 8. My minimum value is negative 9. And I draw something like this. So these are two possible ways that we can have our graph, basically. Okay? Now the first question says, what is the maximum value if, right here, now you may remember what this is saying is that all x values become positive. All x's are now positive. So how does this affect our graphs? You might remember, you might be asking. So what this is saying is if here is x positive, here is x negative. Well, if I were to graph it again, here I get all x positive values, but over here it's also my positive x values. So in other words, this is a mirror of the y-axis almost. So my x values are starting here. Remember, 8's up here. I'm starting below 8, and I'm going to -9. Well, my x negative now becomes x positive. So where this was like x equals -1, gave me this value, this is now x equals +1. Well, +1, I'm up here. So at +1, I'm going to be back up here. So it's going to kind of reflect around the y-axis. Right there. Now notice, would the maximum value be 8 again? Of course not. And we can kind of see that. It's not going to be 8 again. It's going to be whatever that y-intercept was. So this is not going to always be true. They want to find out which of the following must be true. And A, not necessarily true. So I already don't even have to check the second one. What about this? The maximum value of my y's will be 9. So this is saying that all y values are now positive. So what happens is we're going to reflect anything below the x-axis becomes positive. So let's take a look at what's going to happen here. Well, if my minimum value is -9, if I reflect anything below the x-axis, that's going to be reflected up here, which would make my value 9. So the first example works. What about over here? Well, if I reflect everything below the x-axis, same thing. It's going to go up to a +9. So this one will work. And this one says the minimum value of the absolute of f of the absolute value of x is 0. Well, again, if I just go back to here, well, clearly my minimum value up here is not 0, so this one won't work. So the only one that will work is B. That's a tricky one. Try that one again if you need to. All right, question number 4 is just an example of how we kind of see the AP using critical numbers. It says, given the function, right here, 3x cubed minus kx squared, for what values of k do we have a critical number at x equals 2? So they're saying at x equals 2, we know the derivative is 0 right here. Again, that's a polynomial function, so its derivative is never going to be undefined. It's just going to be 0 right there. So we need to take the derivative, and that's what we're going to do here. F prime of x would equal 9x squared minus 2kx. Now we're told that f prime of 2 is 0, so I can plug that in. So at x equals 2, we know the derivative is 0. So I can just plug that in. I mean, 0 equals, this becomes 9 times 4 minus, that just becomes 4k, and therefore, if you're good, k is just 9. You will see this question on tests, quizzes. You'll see questions similar to this on the AP. It's a really good question test for critical numbers right there. All right, for number 5, this is a great question that you should not ever miss. It says the graph is twice differentiable. That means you can take a second derivative, which means it's going to have some sort of concavity values. Which of the following is true? Notice they're asking us the value at 2, the slope at 2, and the concavity at 2. So, and they just have it in different orders. So I want the value at 2, the derivative at 2, and the second derivative at 2. And I want to find out how is that going to affect, and which of those would be first from least to greatest. So if I'm looking at the value, that's right here, the value at 2, well, what is that? Well, x equals 2, this is my x-axis, the value is 0. Now I want to talk about the slope. I don't really know the slope at 2, but I do know that this is negative because it's going down. The second derivative is concavity. Well, this function at 2 is opening up. And we know that the concavity, therefore, because it opens up, is 2. Because this is concave up. And then they just want us to order them. Well, which is the least one? That's my derivative. f prime of 2. What's next? 0. So my value is next. What's after that? My concavity. The second derivative at 2. And that's the order, and I just try to match that up, and it looks like it matches B. Don't miss that one. You're going to get that one really good. All right, everybody's personal favorite, must, mights, or nevers. Now, we've talked about this. The secret to a must, might, or never is always to assume the first part is true, and then you're going to try to prove the second part is wrong. So let's see here. We are told that the function has a relative minimum at x equals 3. Then they say that the derivative must equal 0. So what they're saying is that this is going to be true, that we have a relative minimum, therefore we have to have a critical number. So we have to think, is this always going to be true? If we have a relative minimum, will we always have a critical number where the derivative is 0? Where they're saying that the slope must be 0? Well, let's think. Well, what is our definition of a relative minimum? Well, we need our critical numbers, where the derivative is 0 or D and E. Remember, a relative minimum could be a corner, or it could be a smooth, like a parabola. So they're saying that it just is only going to equal 0. This is a might be true. And the reason for that is because this could be D and E. In other words, remember, we could have a cusp where the slope does not exist, or we can have something smooth where the slope is 0 at the bottom. Both of those would be relative minimums. This one says if the slope is 0, less than 0, so on A to B, we are told that the function is decreasing, then the function is concave down. This is a tricky question. They're saying that the function is concave down, so they're talking about the second derivative here. So think about what a decreasing function looks like. That's a decreasing function, and it's concave down. But I can also draw a decreasing function like this, where it's concave up. So draw it. There's concave down. Here, we have a negative slope. That's a weird looking positive slope. Over here, we have a negative slope. So we have it decreasing on part of it, but not on the whole picture. So this is just a might. It might be depending on which part of the function we're looking at. So in other words, the derivative and the concavity really have nothing to do with each other. They're more indirect relationship. So one does not really necessarily determine the other. Next one, if the derivative is 0, so they're saying that we have a critical number, and the second derivative is less than 0, well, we know what this is. This is saying concave down, so I draw concave down. Then f is a relative minimum. Well, think about that. We just drew something concave down. We have a maximum value here. So this is going to be a never. Okay? So I hope you enjoyed part 2. I'll see you guys later. Bye-bye. Hey, you.
Hey, what are you doing?
Just finishing up my video.
Okay, all right. I love you. Okay.
I love you too.
Okay, I'll chat with you later. Okay?
Are you okay?